Mass relationships and chemical reactions. We're going to look at reaction stoichiometry. Now the coefficients in a chemical equation will tell you either molecules or moles. We're going to use them for moles, and we're going to actually pull out conversion factors from those moles. So 2 moles of H2O equals 2 moles of hydrogen. We can use that as a conversion factor. And the same thing with those other coefficients there as well. We can do a mole-to-mole problem. Go back to the previous balanced chemical equation. We always start with a balanced chemical equation, but we have 3.3 moles of oxygen. We're already in moles, so if you go back to the balanced chemical equation, I can go from moles of oxygen to, in this case, I'm going to go to moles of water. And this is where we use the coefficients. And then from the previous balanced chemical equation, it was 2 moles of water for every 1 mole of oxygen. Your moles of oxygen will cancel out, and that's really all I need to do on this particular problem. 6.6 moles of water would be formed. We can do mole to mass. If I have 0.2 moles of CH4, and I want to determine how many grams of water. I'm going to start with the 0.2. And since I'm in moles, I can go ahead and do my mole-to-mole ratio. I'm going to go from moles of CH4, and I want to convert back to moles of water. So go back to your balanced chemical equation, and this is where I switch substances from CH4 to water. It's 2 to 1. I have moles of water, but I want grams of water, so I need to add in one more step and get the molar mass. For water, 1 mole has a mass of, from the periodic table, 18 grams, and that will cancel my moles. So I would form 7.2 grams of water. And then finally we can do a mass to mass problem. 14 grams of lead oxide. I want to know how many grams of lead will form. I'm going to start with a 14 of lead oxide. I have to go back to moles. Moles is my intermediate. So I need the mass of lead oxide from the periodic table in 1 mole. The mass is 223 grams from the periodic table. I'm in moles of lead oxide, but I want to switch substances. I want to go back to lead. Again, the mole-to-mole ratio, that's where you use your coefficients. And there's 3 moles of lead for every 2 moles of lead oxide. Now I'm in moles of lead, but I want grams. So go back to the periodic table, find the molar mass of lead. So in each of the problems so far, I've just added 1 step each time. But how many grams of lead will form? Just do the math. 19.5 grams of lead. Okay, mass to mass of a mixture. We have an alloy that consists of aluminum and copper, but only the aluminum reacts, none of the copper. So you'll see copper's not even in the balanced chemical equation. What is a mass of alloy required? We're going to start with 1.75 grams of hydrogen. Well, since the only thing that reacts is aluminum, I need to go back to aluminum first. So I got grams of hydrogen. We're going to do grams to mole. Now once I get to moles of hydrogen, go back to the balanced chemical equation. I want to go from hydrogen back to, in this case, aluminum, because aluminum is the only thing that reacts in this alloy. So there's 2 moles of aluminum for every 3 moles of hydrogen. I'm going to go ahead and go to mass. So moles to grams. Periodic table mass of aluminum is 27. Okay, now I'm in grams of aluminum. Since aluminum is the only thing that reacts, and the alloy is 95% aluminum, that means if I have 100 grams of the alloy, 95 grams would come from aluminum. And so there's kind of my setup there from the mass to mass of a mixture. So the mass of alloy, 16.4 grams. Most of the time when a chemical reaction is carried out, there's not enough of one reactant to react with the other. This reactant is called the limiting reagent. It's going to react completely. There's going to be none of the limiting reagent left. The other reactants are present in excess. So let's look at a limiting reagent problem. You'll know it's a limiting reagent problem because I'm given two numbers. I have 8 grams of CH4 and I have 48 grams of oxygen. The fact is, one of those is going to run out before the other. I want to know how much CO2 can be produced. Now, there's a couple ways to go about these problems, but I'm going to choose the simplest way. I'm going to actually set up two separate equations. I'm going to start with 8 grams of CH4, and I'm going to start with 48 grams of the oxygen. And we're going to convert both to grams of CO2. So we have 8 grams of CH4. We're going to do the molar mass of CH4, 16 grams per mole. And I want to go from CH4 to carbon dioxide because that's what the problem asks. And so go back to your coefficients. It's 1 to 1. Once I get to CO2, I actually want to go to mass, 44 grams per mole. I'm going to solve that one. So that's going to be 22 grams of CO2. Let's do the same thing at the bottom. We have 48 grams of oxygen. We're going to convert grams of oxygen to moles of oxygen. Molar mass of O2 is 32. Okay, so now I'm in moles of oxygen. And I want to go to CO2, same product. Mole-to-mole ratio is 1 to 2 in this case. And then the last step, since I'm in CO2, is exactly the same, 44 grams per mole. So the mass of CO2 that would be produced in this case would be 33 grams. So the question is, what mass of CO2 can be produced? Well, I always pick the smallest number, so this is the mass that can be produced. The limiting reagent in this case, although the problem didn't ask, the limiting reagent is the reactant that produced the least amount, which is CH4. CH4 gets used up completely. There will be excess oxygen. I started with 48 grams. There's going to be excess oxygen left over at the end of this reaction. So you always pick the smaller number. Theoretical yield is the quantity of products calculated to result from given quantities. So the theoretical yield is a calculation. The actual yield is what is actually produced, and you would have to be given this number. The actual yield would be produced in a laboratory situation, and the percent yield is simply taking the actual divided by the theoretical times 100. So I'm giving you a balanced chemical equation here. I want to know the theoretical yield, actual yield, and percent yield. I've got 32 grams of CH4. I'm given a mass of CCl4, and I want to know those three yields. Anytime you're given a product, that is the actual yield. So the actual yield, again, you will be given is 167 grams of the carbon tetrachloride. That is what is actually produced in a laboratory situation. I need to determine the theoretical yield of CCl4. And I'm going to do that starting with 32 grams of my reactant because I have excess Cl2. So I'm going to start with 32 grams, convert grams back to moles. So I need the molar mass of CH4, which is 16. do your mole-to-mole ratio. I want to convert to CCl4 from CH4. And the mole ratio is 1:1. Once I get to moles, go back to grams, and this will be my theoretical yield. The molar mass of CCl4, 154. So my theoretical yield is 308 grams. That's how much could theoretically be produced from 32 grams of CH4. But you will never get more than the theoretical yield. So the percent yield is simply how much I actually got, which is 167, divided by what I could have gotten if the reaction were 100% complete. Multiply by 100. The percent yield in this case, just a little over half, 54.2% yield for this reaction.